So we said that a vector has a length or a magnitude, um, but how do you get it? So let's say you have a vector which is introduced to you in its component form. That is, the vector is told to you as left angle bracket, a number, comma, a second number, and then close angle bracket. We're assuming the 2D case right now. So you have a vector that's told to you in that format, but since a vector by definition has a magnitude and a direction, what is the magnitude? How do you compute it? Well, we have a formula. By the way, you'll hear me use the words length, magnitude, and norm interchangeably. There are three words that all mean the same, at least in vector land. And for notation, for the length or magnitude or norm, there's two notations. Our book happens to like just using a single vertical bar around each side of the vector itself. I happen to personally like a double vertical bar to the left and to the right. Uh, the only reason I guess I like this is many books tend to use that. That's all it really is. You might look at this and say, oh, the single vertical bar, am I going to confuse that with absolute value? It'll never occur. As long as you keep in mind what you have as a vector, how could you confuse this with absolute value, right? Because absolute value is just for a real number. And then the formula for this is square root of square of the first component plus square of the second component. Again, just the comment I mentioned, the Stewart textbook uses a single vertical bar around each side. There's no way to confuse this because the object between the vertical bars is a vector. A lot of books do use the double vertical bar with the bold vector v. So you've got lots of choices. When we're talking about magnitude, use a single vertical bar on both sides, use a double vertical bar on both sides, draw the bold v if you're doing something like LaTeX, if you'd like, or draw the arrow above if you're handwriting. There's so many different ways to write these things. I hope this formula looks kind of familiar, looks a lot like the distance formula, and the reason is that both the distance formula and this magnitude formula come from the Pythagorean theorem. So I have this small example here in an app. Of course, there's this point, 5.8 comma 3.62, 3.64. And that's the point, right? In blue, here's a point. If I want the vector in red, that vector is shown down here in angle bracket format. It's maybe hard to see on screen, but those really are angle brackets for the vector v. And the thing is, well, the length of this vector, I mean, like literally how long is that vector as drawn? Well, it's the hypotenuse of a right triangle. So no wonder the Pythagorean theorem shows up here. Okay, so small example on the slide. If the vector v has components 3 and 4, then when you compute the magnitude, you should get the number 5. If you have the vector w is 3, 4, negative 2, we haven't gone through all the steps, or I haven't even shown you a complete reason, but it's maybe not surprising that the magnitude formula would include the squaring of the third component as well. A vector whose length is 1 is called a unit vector. So for example, if you take the vector u to be 3/5 and 4/5 as the two components, then when you compute the magnitude of this vector using that magnitude formula, you're going to get the number 1. Therefore, the vector u as defined in this example is a unit vector. Here are a couple more examples of unit vectors. In fact, if you just have, in 3D space, if you have a 1 in one spot and zeros in the other spots, these are called the standard unit vectors, which also go by the name I, j, and k. Be sure to have the arrows above on each of those.